thoughts about the topic of quantum physics before we get to quantum biology proper, because there's something that is very important to stress, and when you read about quantum biology, quite often people forget that quantum physics is not just about a single particle hitting another particle or a finite number of particles in an atom, but it also applies to huge numbers of particles, and that's why you use statistics. And quantum statistics is something very important to keep in mind, and probably you, if you come from the life sciences area, you're familiar with the Boltzmann statistics, the Arrhenius relation, things like that. And these things are based on classical concepts. But in quantum statistics, there's two differences, at least. So in the classical case, when you have particles at different energy levels, they will occupy these energy levels inversely proportionally through the exponential function, by the way, to the energy. So the higher energy, the lower probability of that particle being there. And the tendency of all physical systems, with no exception, is to occupy the lowest energy state, which is called the ground state. And that's kind of a law of physics, which is the most fundamental minimization of energy. But how it's occupying it, it depends on the nitty-gritty. And in this case, for quantum systems, I mentioned to you the presence of spin, a new variable that doesn't exist in classical physics. And there are two groups of particles called fermions, from Enrico Fermi was the Italian physicist who worked on that. And these are spin half integer, 1/2, 3/2, 5/2, and so on. And these are called fermions, or Fermi-Dirac statistics. And in this case, fermions, like electrons are fermions, and protons, they cannot occupy the same energy state. As simple as. So you can see here, each energy state occupied by one fermion. And that explains, actually, without this, we wouldn't know the Mendeleev table of periodic elements, because this is how you occupy energy states in an atom or molecule, right? Atomic levels, you have orbitals, and it's the only thing here, if you had spin, 1/2 could be spin up and down, so you could have two particles at each energy level. So that's one, like in atomic physics, you have 1s, 2s, 3s states, right? And you have occupation of two, because up, spin down, right? Do you remember that from chemistry? Maybe. And all right. And so on. So that explains how you build up, how you fill up the atomic orbits. In other words, without spin, there's no atoms. That we can explain anyway. And the other case is bosons, or Bose-Einstein particles. And in this case, they actually have the opposite tendency. They really prefer to be together, and there's no limit on the occupation number for energy states. So bosons have a very interesting property, which is called Bose-Einstein condensation, and that means that macroscopic number of quantum particles can occupy the lowest energy state, which is quite interesting. And a lot of people speculated that this is the basis of biological coherence, that there is some sort of transition to being in the same state. Okay, so Maxwell Boltzmann gives Arrhenius, it's the same kind of thing, e to the minus beta e is the energy, beta is 1/kT. These are fermions and bosons, and that applies to. So why am I mentioning this? That applies to these collective states in large numbers of particles, for example, crystal lattices. Crystals, you can hold it in your hand, a piece of crystal is a quantum object. Its vibrations are quantized, called phonons, and they obey Bose-Einstein statistics. Okay, that's an interesting anecdote. I like to throw in anecdotes because it probably helps you remember some of these characters. So Bose was a noted Indian physicist, and he came up with this idea of Bose condensation. We now call it Bose condensation. And so introduced quantum statistics, And it says here, he wrote the paper, which was rejected, but he believed in, wrote to Einstein, and Einstein endorsed it, and it was published, and now we call it Bose-Einstein condensation, or Bose-Einstein statistics. Right? So sometimes you need a godfather, even in physics, to make it to the top. But Bose, I don't believe he got a Nobel Prize. Einstein did, and as I said, should have been given 3, at least. Yeah. Oh, but he got a Fellowship of the Royal Society, which to some is even more important than a Nobel Prize. Was nominated a few times, never got it. And then now, of course, we have experiments confirming the existence of bosons, helium-4 superfluids, for example. And these experiments, which took place, let's say, 50 years or 60 years later, also garnered Nobel Prizes to the experimentalists. It's kind of ironic, right? The guy who came up with the idea didn't get it, but those who proved it got it. All right. So these are the functional forms for the probability distribution of occupying a given energy level. I know you're not into sort of math, physics, but for completeness, if anybody wants to know, this is it. And if you compare it to classical case, Maxwell-Boltzmann, it would be 0 in this formula. So it's kind of nicely symmetrical. 0 in the denominator for classical, -1 for bosons, and +1 for fermions. And as I mentioned briefly last time, this gives rise to explanations for semiconductors, because they are characterized in terms of their occupation levels, to the valence levels, and then conduction level by these Fermi-Dirac statistics. So we couldn't have semiconducting technology without knowledge of this important piece of physical information. And that's temperature dependence of it. So at different temperatures you have a different probability distribution. Okay, and then you can plot it as a function of energy, and you have classical in the middle, Bose-Einstein at the top, and Fermi-Dirac at the bottom. So you eventually spread out. Well, even both for bosons have a tendency to stay at the lowest energy level, but as you increase the temperature, they tend to occupy higher and higher energy levels. Okay, so that leads us to the question of, is quantum mechanics applicable to microscopic systems that we have intuitive understanding from everyday experiences? And indeed, there are not that many, but there are notable examples of quantum microscopic systems, which include superconductors. Again, that goes back to the 1920s, discovery of superconductors. The question, of course, is how high a temperature would have to be to destroy superconductivity, because they are fragile systems. And for now, I think it's something like -150 Celsius. So you don't have superconductors at room temperature. If you were to argue that humans or living systems are quantum, then that's a common argument to say, yes, but we exist at physiological temperature, 37 degrees Celsius, which is, almost 200 degrees higher than superconductors. Superfluids even lower, like up to maybe 4 Kelvin or something, which is 0 Kelvin is -273 Celsius, so it's very, very low. But laser, I guess I mentioned lasers. Lasers are quantum devices. They really operate on the principle of quantum transitions of electrons emitting photons, electromagnetic waves, at a very sharply defined frequency. So the one difference I want to emphasize here is that all these examples, except for lasers, are examples of equilibrium. That equilibrium means that you allow the system to reach its steady state or stable state. But living systems are never at equilibrium. A living system at equilibrium is dead. So this is one crucial difference between physics and biology, right? Biological systems, to be alive, must be out of thermodynamic equilibrium. And lasers operate out of thermodynamic equilibrium, because you have to pump them with energy, and then the energy that allows the electrons to go up is returned in the form of coherent light, red or green or whatever. I don't know, this one, green, right? Because of the energy pumping that starts the process. Without this, that wouldn't happen. You would only have white light. Semiconductors I mentioned, phonons I mentioned, and magnetism I also did, and spin is necessary for the existence of magnetism. Okay, so just to finally put a nice ribbon over all this quantum physics business, we started with quantum mechanics. First, these early observations, things were not really explainable using classical concepts. So Max Planck introduced the concept of quantization of energy, and Bohr applied to atoms, and then we have all the beautiful application of quantum concepts to chemistry, molecular physics, and semiconductors, condensed matter physics. But that's going up on the scale of size and energy. Going down, physics proceeded for the next half a century to gradually explain smaller and smaller pieces of the puzzle, subatomic particles, which involved interactions of light and matter in the form of quantum electrodynamics, subatomic forces, weak and strong forces, eventual quantum chromodynamics, with the completion of this edifice by putting in quarks and gluons, and now the so-called standard model, and the Higgs boson, you may have heard, was confirmed experimentally, which is kind of the glue between these quantum particles. And so that's almost complete. One thing that is not explained, so this is kind of a powerful statement to make: quantum physics explains everything, in principle, except gravity. So the force which is to us probably the most intimately accessible, gravitational force, you can feel it if you get hit with a falling rock or a flower pot from the second floor balcony. Quantum physics really cannot yet incorporate in all of this. But other than that, pretty much everything is explainable and even predictable. So Dirac predicted the existence of antimatter because it was simply on the basis of symmetry of equations and solutions with positive and negative charges were equally probable to be obtained from these equations. So he predicted there must be antimatter before it was confirmed. Now we know there is antiprotons and positrons and antineutrons. All of this took a few decades to demonstrate. So that is actually quite different. I want to make a sociological observation, a sociology of science, that in physics, and that era actually produced something which is now also called theoretical physics. Theoretical physics is actually considered to be the most abstract and the most respected area of physics, because you can use just your mind, like Einstein did, and make incredible generalization about the universe, like the curvature of space, time, the finite speed of light, or the existence of quantum states, and so on. Biology, sadly, I have to say, has no respect for theory. So this has to change. Maybe quantum biology is the direction to go in order to get respectability. So anyway, that was my 2 cents worth of historical critique. Okay, this guy, so Janos Neumann, or John von Neumann, was mentioned before. He formalized quantum mechanics and also laid the foundations of quantum information theory, which is now being used for quantum computing, and worked on cellular automata, which is a very interesting branch of computational mathematics. And introduced the ideas behind the digital computer before they were even constructed, and also worked on surface application in biology, because that's, you know, one of the most important questions. How did the first living organism arise? So it has to be replicating. And that leads me to the concept of, well, maybe I'll come back to it, but the concept of, again, what is life? That's Schrodinger's, you know, book was titled like that. And what is special, or maybe I'll ask you, we'll take a little quiz here. What is, in your opinion, the most important quality of living